the So before we start a new problem, I just wanted to go over some things that to clarify some things from the problem that we did yesterday. So the problem said find the absolute minimum and maximums of the function f x y is equal to x squared plus 4y squared minus 2x squared y plus 4 on the box. So here's your, let's say, here's x and y, and here's your box with y varying from -1 less than or equal to y less than or equal to 1, and x also varying from -1 to 1. And so one thing, so we said we need to find the critical points inside of this domain, which we did. We also need to find the critical points on each boundary. So if this is D1, D2, and so on, let's say D3. And D4, we need to find the critical points on each line, which is done by figuring out what the single valued function for f is there. Now, for example, we found on D1 the points negative square root of 2, comma -1, and the square root of 2, comma -1. And some people asked why these critical points aren't in the computation for the points that we plug in. And that's because one of them is somewhere here and one of them is somewhere here. The square root of 2 is bigger than 1. So it's not in this domain. So you ignore them. So even though there were critical points that are on this line, they're on this type of line, something like this, they are not in the box. And then lastly, we said each one of these points is also a critical point. And you also have to compute the value of f for each one of these. And that's the last part of this problem that I wanted to talk about. Are there any questions about this? Okay, so let's move on to another problem. So let's say our f xy is equal to 2x squared minus y squared plus 6y. And we are on a disk. So here's our domain. And it's the domain x squared plus y squared is less than or equal to 16. So because of this less than or equal part, you're talking about this entire interior. And your boundary, of course, is when you're equal to 16. And this is some circle. Any questions so far? Okay, so the first part is to take the gradient of f at xy and set it equal to 0. So this is going to be 4x and -2y plus 6. And we want this to be equal to 0, 0. So we have 4x is equal to 0 and -2y plus 6 is also equal to 0. So this tells us first that x is equal to 0. It also tells us that negative, so it tells us that 2y is equal to 6, which tells us that y is equal to 3. So we should have the critical point 0, 3. Any questions about this so far? Okay, so that's some point in the interior. Let's say this point. I mean 0, 3. Actually, so it's this point over here. So that's one of our critical points, and we have to keep that in mind. Now, what about the domain? So on the domain, again, we want to turn f into a single valued function. So in different situations, you might do different things. Of course, you can put cosine and sine in here, right? Take x to be cosine, or 4 cosine, y to be 4 sine. And that might work, and then you plug your cosine and sine into here, and you have something with respect to t. So all that might work. But another thing, but solving for the cosines and t's and sines of t's might be hard. So instead, what we can do is we can say, okay, if on the boundary, my equation is x squared plus y squared is equal to 16, and I really only have x squared. I don't have anything in terms of x or x cubed or anything like that. So I can say that x squared is equal to 16 minus y squared. And now I can just plug that into here. So now my new f, and now it's just f with respect to y, is going to be 2 times my x squared. Well, my x squared is this, just that. So 2 times 16 minus y squared. So 32 minus 2y squared minus y squared plus 6y. And this, of course, is, so this is going to be 32 minus, so let's do that in the last part. This is going to be negative 3y squared plus 6y plus 32. Okay, any questions so far? Yeah. The how do I get what? Sorry. Oh, the f of y. So again, this is for the domain. So let's say on the domain D, let's call it D1. So that's this boundary over here. That's this boundary, right? We found the critical points in the interior. We want to now find it on D1, the boundary. So what is the boundary? So we know that the entire disk is given with this equation. So on the boundary, we have x squared plus y squared is equal to 16. So this is only a function that in terms of x only has x squared. It doesn't have any other thing. So we can just say, okay, what is x squared? X squared is 16 minus y squared, right? Well, once I have this, I can plug it into my function. I can take my x squared and I can plug it in right there. And that's how I get the function only in terms of y. Any other questions? Okay. So now we can also note that if this is your x, And this is something that we'll start doing more and more often with integration. So it is useful to pay attention to. We need to be able to tell what are the parameters that we allow y to be. So from where until where can y go? What are the extremes for y? So y goes from down here. Y goes from down here, right? That's the most extreme that it is at -4, all the way up here to 4, right? Those are the parameters that you have for y. Of course, sometimes x is positive, sometimes it's negative, but y goes from -4 at the bottom part up until 4 at the top part. So we can also say that we have boundaries over here. It's not this entire function. The boundaries are y goes from -4 less than or equal to y less than or equal to 4. Those are the boundaries for y, right? Y is not going to go on forever. It's stuck between those two boundaries. Right? Because of course, if we allowed y to get bigger, then we won't be on this disk anymore. We allow y to be bigger, then of course we're just going to leave the disk, which we don't want. So we fixed our y. Now that we have this, we can solve the last part of the problem, which is find the critical points on this boundary. So we take f prime of y, which is equal to -6y plus 6, and we set this equal to 0. So that tells us that -6y is equal to -6, which tells us that y is equal to 1. Now, when y is equal to 1, how can we figure out what x is? Yeah, plug it in to this equation over here or into your boundary, but this equation, we would have x squared is going to be equal to 16 minus 1, right? So that tells me x squared is going to be equal to 15. So x is going to be equal to plus minus the square root of 15, which is less than 4. So those will be points. So we can say, okay, now my critical points are 0, 3, and then we have negative square root of 15 and 1, and the positive square root of 15 and 1. And then finally, we have 2 more critical points. Can anyone point that out to me? Yeah, so the critical points are when your y is between -4, when your y is -4 or when your y is 4, because those are the boundaries of this one-dimensional equation, and you have to keep that in mind. So the other critical points are going to be 0, 4, and 0, -4. So these are all your critical points.
Wait, is there not 4, 0, and -4, 0?
No.
Why not?
I mean, there aren't any boundaries with respect to x. There's nothing that would give us those points. Yeah.
So where did you find the uniform?
So in a one-dimensional equation, you need to consider the boundaries when you define your critical points, right? So if you have some function, here's your function f of x, and I ask you for the absolute value, minimum and maximum in this interval, right? So you find the critical points in the interior, and then these points are also critical points, right? So when we're doing this problem, this is a one-dimensional problem, function only with respect to y. And this over here is the boundary. So that's these points over here. So they have to be taken into account, right? Now, when y is -4 and 4, what is x? So you go back to the main equation for your boundary, and you plug in, let's say 4 here, and you get that x is 0. You plug in -4 to y squared, right? 16 minus 4 squared is also 0. So you get that your x's are 0, and that's how you get these points. Okay. Yes.
If you solve your boundary equation for x instead, wouldn't you check the x?
You would, but the real problem with that is that you have this y here. And if you had some equation with respect to x, you wouldn't be able to deal with that y. So you would have, let's say, y squared is equal to x squared minus, sorry, -x squared plus 16. That won't work. And if you take the square root, y is equal to plus minus the square root of this thing. Well, now you have these two different, you can do this. You can break up your domain in the bottom part and the top part, and then you need to, so let's say this part is the top part. Let me redraw the domain. So you can solve it this way, but it's a little bit more tricky. So here was our original domain. These equations break it up into the top part with the plus. So this corresponds to the square root of -x squared plus 16. And we can call this D1. That's your first component of your boundary. And then the bottom part, which is D2, which is, let's say, negative square root of -x squared plus 16. And then, of course, you have two critical points here and here at the boundaries of your boundaries, right? These boundaries are two-dimensional boundaries of the, sorry, one-dimensional boundaries of this two-dimensional space. So here's your two-dimensional space, and these are one-dimensional boundaries. And then they have boundaries, which are these points over here, this point and that point. So then you have to check those points as well. So those are then critical points. Does that make sense? Any other questions? Yeah. It's just because there's only an x squared. And you do have to find the same type of critical points up here and down here, but that's because your y is fixed, right? Your y is bounded. So you still have to be paying attention. All this type of stuff just appears in different ways, and you just have to pay attention to where your critical points can appear. Yes.
Wait, so there's only an x squared, there's a y squared?
No, with respect to x, there's only an x squared. There isn't an x. So if I just set up this equation over here, x squared is equal to 16 minus y squared, I can plug that into the x squared directly without having to do anything else. If I try doing the same thing with respect to y, because I have a y here, I can't just use y squared, I will have to use y. In order to use y, again, you can do it, but you have to break it up into the top part and the bottom part. You can also use cosines and sines, and that will work too, but it might become more complicated to solve the arithmetic later on when you take your derivative in terms of sines and cosines and set it equal to 0. That might be a harder thing to do. I don't know. Yeah. Yeah, here are the critical points. Let me just make sure. Okay. Okay, anyway, the last step that you need to do is you need to plug in these points into your F. So you need to plug them all in, see what values you get. The higher values, so I can say some of this, so let's say F of 0, 3 is equal to 9, okay? Let's do one more. F of the negative of the square root of 15 and 1, that is equal to 35. And so then if you just check these all individually, you would find that this point gives you the value negative 40. And so one second, and then your minimum is this point over here. This point is your minimum, and it gives you 8. Okay, and that's your absolute maximum is this point, absolute minimum is that point. Any questions? Yeah.
So if we did solve it using the X instead, we wouldn't have done those critical points. But
No, you would. You would get these critical points, yeah. I mean, you can try it. Okay, any other questions? Sorry, again. Negative 4, just negative 40 is a number. What do you mean? Oh yeah. Oh, sorry. This okay. Negative. I thought it was 40 for a second. This is the absolute minimum, and so then the maximum is the one with 35. So that's these two. So these two are 35, and that's the absolute maximum. Thanks. Okay. Any questions? Okay. So then let's move on to Lagrange multipliers. And the intuition behind what we're trying to do for Lagrange multipliers is the following. So if you have some restriction, so let's say you're restricted to this curve over here, and it's the curve x squared plus y squared is equal to 4. So that's a curve. And then we have some function, f of xy, let's say is equal to x cubed plus y. That's what it is. So it's some function that, so here's my x, here's my y. It's in 3-dimensional space. So let's say this is my f, and here's my curve at the bottom. And we would want to know what is the maximum and the minimum of f, but restricted to this curve, on this curve. Okay, that's the question the Lagrange multipliers aims to answer. What is the maximum and the minimum of this function restricted to this curve? And so what we can try to do is we can try to think about what happens at the absolute minimum and maximum. So let's think of the level curves of f. So let's imagine that this is one level curve of f, and here's another level curve of f. Maybe they does something like that. And let's say here's another level curve of f. Okay, probably not drawn to scale, but these are all level curves of f. Now, what happens at the absolute minimum and maximum? Well, what we can say is, let's imagine that these level curves are something like this. This is 0, this is 1, and this is 2. Can anyone tell me where is the maximum of my function f? Where does the max happen? On the purple curve. At 2, yeah, and right up on this intersection, right here. This is the maximum, right? No. It's at the level curve 2. You see, this is your level curve 2, but we're restricted to this curve over here, right? We can't leave it. So where's the maximum on the purple curve? It's this point right here, right? This point is somewhere between 0 and 1, right? The level curve above it is 1, the level curve below it is 0. So it's some point between 0 and 1. That's not going to be your maximum. Your maximum is this point right here. Well, what happens at this maximum? Well, the gradient of, let's imagine that we rewrite the this in terms of some function, g of xy is equal to x squared plus y squared minus 4. So we write something like that. Well, then the gradient of g, well, the gradient is going in the direction of greatest increase. So it's some vector like that. It's orthogonal at 4, maybe, yeah, let's get rid of this 4. The gradient of g at this point is, we can now imagine that the purple curve is a level curve of g, so it's orthogonal to that level curve. And the same thing is true for f, right? The gradient of f is also orthogonal to the green curve, right? Because it's a level curve, so maybe it looks something like this. Yeah. Because we don't want to think about this function. We don't want to think about the 4. We want to create a function whose level curve is this purple level curve right over here. So of course, when this is equal to 4, right, we get this equation, and so then that becomes the level curve. So we're trying to think about the function whose level curve is this purple curve that we've been talking about. But we can see that the gradient of g, so let's say the gradient of g at x comma y, right? So that's this vector over here. It's orthogonal to the level curve of g, which is this purple curve, is equal to some constant, right? The gradient of f might be bigger or smaller, but it's equal to some constant times the gradient of f at xy. Because this is the gradient of f at xy, right? It's orthogonal to the level curve, the green level curve, right? Because gradients are orthogonal to level curves. And so because these are going in the same direction, we can write this equation. Similarly, the same thing happens at the maximum. What's the maximum over here? This point over here is the maximum, right? The level curve is 0. The green level curve is 0. And it's whenever it touches the purple level curve, that's the best place that you can get the lowest point. And you have the same thing happening there, that the gradient of of g is parallel to the gradient of f. Now, remembering this picture is not very important. What is important is to remember this equation over here, which is when you have a restriction g, so when I have some curve, so let's do it with this example. I can set up this equation, and if I solve this equation, I will find my maximum and my minimum. So let's do this as an example. So what does this tell us? It tells us that, so we want the gradient of fxy, and I'm just going to move the lambda to the other side because that's how we do it, is equal to lambda g xy. That's the formula, where g is my restriction and where f is my function whose minimum and maximum I'm trying to find. Okay, so what's the partial of f with respect to x? That's 3x squared is equal to lambda times my gxy. So this is my gxy. So times 2x. right? That's my first equation that we get from the partial with respect to x. My second equation, partial with respect to y, is going to be 1 is equal to lambda times 2y. Any questions so far? And then generally the last equation that you use is this equation over here. And this is, by the way, why we have been putting on the homeworks solving the system of equations with lambda. It's because that this is that exact thing. So for number 3, we have the equation x squared plus y squared is equal to 4. That's our third equation. So now we have 3 equations and 3 unknowns, right? X, y, and lambda are the unknowns, and we have 3 equations. So let's see if we can solve this. So first we can say that either x is equal to 0. So let's go x is equal to 0, or I can divide by x in my first equation, and I can get 3x is equal to 2 lambda, right? So let's break these up. First, let's imagine x is equal to 0. Well, if x is equal to 0, I can use this equation, and I can say that my y squared is going to be equal to 4, which means that y is equal to plus or minus the square root of 4. So I get 2 critical points here, and those points are the points 0 and plus or minus the square root of 4. Any questions so far? Yes. So I'm saying either or. Either x is equal to 0, in which case I cannot divide x here. I can't divide by x. But I can say, okay, x is 0, in which case I can use this equation and figure out what y is by plugging x is equal to 0. Or x is not equal to 0, in which case I can divide by x. And so then I get this side. Okay, let's work on the second part. So if x is not equal to 0, we get that x is equal to 2 lambda over 3, right? We don't know what lambda is, but x is equal to 2 lambda over 3. And from this second equation over here, from this equation, we get y is equal to 1 over 2 lambda. Any questions? Okay, once I have these 2 things, what can I do to try and solve this problem? Yeah. Plug it into the third equation. So we get x squared, which is 2 lambda over 3 squared, plus y squared, which is 1 over 2 lambda squared, is equal to 4. Okay, can we solve for lambda? Well, I made the problem up, so it might be a bit complicated, but we can definitely try. So we can say that 2 lambda squared over 9 okay, so we want a 2 lambda squared down here, so that's multiplied by 2 lambda squared, and we can multiply the top by, and we can multiply the top by 2 lambda squared, okay, plus 9 over 2 lambda squared is equal to 4. 9 over 9 is equal to 4. So now we can put these together and we get 2 lambda to the 4th power plus 9 is equal to 4 times 9 times 2 lambda squared. Okay, yeah, solving this is not going to be feasible, but if we could, and we could get lambda, we can plug that lambda into here and get our x and y and get our other critical points. So the way I made the problem, I don't think I can solve it, but the problems that you'll be given will be solving this. So let's do another example. Any questions? Yes. Yeah. Though if you found the x and the y values, you already know your critical points. So you don't really, you can find lambda, but it doesn't really matter. Okay, so let's do, okay. So the type of questions you might be given can be something like find the dimensions of the box. So find dimensions box with the largest value with the largest volume if the total surface area, if surface area is equal to 64 centimeters squared. Okay, so these are types of problems that you can be asked. So what you need to do is you need to realize that you're trying to maximize the dimensions of your box. So what's the maximize the volume of the box. So you should write down the equation that gives you the volume of your box. So the volume of your box is f of, let's say, xy. So this is a box with the x-axis being x and the y-axis being y. Okay, so that's your box. So what is its volume? It's going to be equal to x times y, right? So this is a three-dimensional, well, it has 2 independent variables and 1 dependent variable z. And for any x and y, it gives you the volume of your box. Now, of course, I can take this to infinity if I wanted to. I can just blow up x and this thing goes to infinity. But I have a restriction, which is my g. So I have something in the form of g of xy is equal to, so what is my total surface area? So if I take my box, here's my box, I'm going to have 2 maybe, do they want the z? Give me a second. Yeah, so sorry, this is a 3-dimensional box, so 3 dimensions. You also have a z coordinate. Any questions so far? So yeah, this is your volume if you have a certain amount in x direction, certain amount in the y direction, and certain amount in the z direction. Okay. So what's your surface area? Your surface area is given in the form of 2xy. That gives you this part of your box and then the upper half, right? That's why you have 2 of them, right? The surface area is going to count the entire surface. So you have 1 part down here, 1 part on the top in your box. Let me draw a box. Here's our box. This part has area xy. This part has area xy. So you get 2 of them. Plus, okay, let's go for, let's say, this one and this one. So what is that? That's y and z. So plus 2 yz, right? And then finally plus And then you have this one in front and the one in the back are 2. But those are 2. And the one in the front is xz, xz, and the one in the back is also xz. So that's our function g. And we want this function to be equal to what? Anyone? What's the restriction for this function? Yeah, 64. So we want this function to be 64. So now we have our f and our g, and we can solve this problem. And again, we use the equation, the gradient of f at x, y, z is equal to lambda times the gradient of g at x, y, z. That's the equation that we're using. Okay? So what is the gradient of f? So let's write out our equations. 1, our first equation, the partial with respect to x is yz is equal to lambda times the partial with respect to x of g. So that's 2y plus 2z. Okay, second equation. Partial with respect to y of f, that's xz, is equal to lambda times 2x plus 2z. Okay, that's our second equation. Final equation, partial with respect to z of f is xy is equal to lambda times the partial with respect to z, which is 2y plus 2x plus 2x. Any questions so far? Okay, and then the last equation we're going to use is the g equation, which is 2xy plus 2yz plus 2xz is equal to 64. So we have, yeah. The right-hand side of these are the derivatives of your g. Yeah, the derivatives of g with respect to x, y, and z. So the derivative of g with respect to x, 2y plus 2z. So 2y plus 2z is the answer. Okay. So this is your system of equations. And you have 4 equations and 4 unknowns, so you can solve this. So one of the techniques that you should have learned from the homework is sometimes you multiply these in order to make them seem similar. So you see we have this yz and xz. Well, if I multiply this by x and I multiply this by y, they are going to be equal. So let's do that. So from the number 1, we get yxz is equal to lambda times 2yx plus 2yz. Okay. From number 2, we get, in the first one, I multiplied it by x. So 2x. 2x. In the second one, I'm multiplying by y. Yxz is equal to lambda times 2xy plus 2zy. And finally, in the third one, I multiply by z, so I get xyz is equal to lambda times 2yz plus 2xz. Okay, so I can set all of these equal, right? And I get lambda times 2yx plus 2xz is equal to lambda times 2xy plus 2zy, which is equal to lambda times 2yz plus 2xz. Now we can assume the lambda is not 0. That is just something we can generally assume. So we can erase the lambdas, and this is what we get, these equations. Now, what is our last equation? 2xy, okay, 2xy, here we have a 2xy, 2xz, okay, we have a 2xz here. Then we have everything else basically repeats. So let's look at the 2xy, another 2xy, and then 2yz over here. So that's, we get one of those, and then another 2yz over here. So another 2yz. So let's say two of those, and another 2xz. So we get two of, so we basically, in these equations, we have two of each one of these. Okay? So what we can say is, we can say the following. Let's take our 2xy and 2xz, the 2xy and 2xz, and substitute it by this and see what happens. So that would give us 2yz from here plus 2xy, so plus 2xy plus 2zy, right? We basically took this and exchanged these two parts with this part over here. And so we got the original part, 2yz plus 2xz, which is this, 2xz plus 2zy. 2zy is there. Okay. Now what can we do? And we know that this entire thing is equal to 64. Okay, the next step that we can do is we can take our 2yz over here and our 2xz, and we can also substitute that into this equation, 2yz over here, 2xz. You can plug that in and get something in terms of 2xy and this new thing. So I am going to stop here and leave it as homework for you to finish this, and then tomorrow I'm going to finish it myself, okay? Lagrange multipliers, yeah, like something simple. Set up the equations, start solving.
What units are gonna be on the quiz tomorrow? Just so I can like review.
Yeah, yeah. Optimization of several variables and the Lagrange multiplier.
It's 14.7. So just don't review anything else there.
So yesterday,